All right, we're now transitioning a little bit out of forces. We're still going to kind of talk about forces, but we are transitioning now into our friend energy. And we're going to be specifically talking about energy flow diagrams, or LOLs, as you may hear them referred to in class. So I've got a scenario here for you, and I'm going to use this scenario to walk you through kind of a complicated series of LO diagrams that'll hopefully cover all the bases that you're going to in kind of our basic world. If you're in honors, we're going to add a little more tricks in, but for regular, this should definitely cover all the possible bases. So, one of my favorite roller coasters is Raging Bull. If you've ever been to Six Flags, Raging Bull is the luxury roller coaster where you don't get banged around when, especially if you're a large person like myself. So we're going to do kind of an LOL for Raging Bull. So we're going to look at 3 points. Points A, which is the very first point that you're dropped from, maximum height before it all gets started. Point B, which if you've ever been on Raging Bull, there's this spot where you kind of almost come to a stop and there's a little wheel, little tire that pushes you. You kind of go through this double dip. We're going to talk about what the reason for that is, at least my hypothesis. And then we're going to talk about point C, which is the bottom of the hill after you go through that dip. All right. So the very first important thing you need to do is you have to decide what you're going to call the ground. Now, if I wanted to, I can call anywhere the ground, but I usually go to my lowest point. And since I am going to be evaluating that point C, and that's the lowest point, I'm going to say this is my ground. So that's what I'm going to call the ground. But if I only went from A to B, I'll be honest, I would make this my ground and I would move up my zero line because you get to do that. Second important thing, you got to pick your system. All right. So my system is going to be the, I don't want to say coaster. What would you call it? It's the cars. All right. So the cars. So not the whole roller coaster. I'm just picking the cars as my system. That way I can talk about some energy lost. So here we go. Let's go through this exciting LOL. So we actually have 3 spots. So we've got L, O, L, O, L. All right, so this is going to be part A, point B, point C, and again, those are the cars, and I'm including the people in the cars, or whatever, just so there's no confusion. All right, so the very first thing we want to do is at any location is simply identify what forms of energy are present. Now at this max height here, we're just going to assume that your velocity is basically 0, because when you're at that roller coaster, you're basically not moving at the very top. They like to do that, so they just kind of drop you. All right? So we assume we have no velocity at that point, which means we have no kinetic energy. But we are definitely above our 0 line, so we definitely have gravitational energy at this point. And since time really hasn't passed, we haven't had time to really lose any energy or anything like that. We have no work being put into the system or out of the system at this point. We just have gravitational potential energy. So then I'm going to make my little bar graph here. And then I'm going to pick a random number because I like to just kind of put some numbers on this so we can see how trends go. And I like the number 12. Now, one thing I do want to mention about this is let's make an assumption here. All right, let's assume that this height right here, we'll call this height, we'll say it's about 40 meters. All right, we'll just say it's about 40 meters. And then we'll say the height at B, which I keep forgetting where it gets kicked, but we'll just say it's here. We'll just say that's 30 meters. All right, and I'll come back to why that is important in a second. All right, so point A, I've decided 12 units of energy. Later on, we'll get into the actual math. But then we go to point B. So you race down here, you get all the way up to part B. What's going on? Well, you're still moving. So you definitely have kinetic energy, and that's the number 3, not the letter E. All right, let's try that again. Okay, so you've got kinetic energy because you are moving. You have a velocity vector. And you're above the ground, so you definitely have gravitation. Now, we're not as high as we used to be, and I have a feeling we're not doing like our max speed here. And in reality, as we went along this track, we definitely lost some energy to the outside world, especially through friction and things like that. Noise, roller coasters are not exactly the smoothest things. So I should also have some work leaving my system because energy left the roller coaster. So, how much energy should I put into gravitational, kinetic, and work? Well, the one that you can make a good assumption on is gravitational, and that's because we know that the amount of gravitational energy you have is directly proportional to your height. So here we had a height of 4 meters, I gave it 12. Now we're at a height of 30 meters, so we're 3/4 of that. So 3/4 of 12 is, you guessed it, that's a 9er. All right, so I know I have to have 9 units of gravitational energy. Now, how much is kinetic? Well, that's kind of up to me. I know I lost something to work, and I know this all has to add up to 12 because energy is always conserved. So 12 minus 9, I got 3 to play with. So I'm going to give 1 to kinetic because I'm not moving super fast at that spot, and then I'll give 2 to work. So 9 plus 1 is 10, plus 2 is 12. We start with 12, we ended up with 12. Energy has been conserved. All right, that's a big thing. Let me go through, so I'm going to mark that. All right, so when you go from 2 points to 2 points, total energy must be conserved. My brain was like, forgot how to spell conserved halfway through that. All right, so now, go back to my purple, yay. All right, so now, what's happening at C? Well, as you go from B, this little dip, one thing I do know, there's a little wheel there, and it gives you a little push. And since it gives you a push, that means we have to have work going into the system because it gives you a little more energy. My belief is because later down the track, they basically realized that the cars were not going over the last hill or something like that, and so they did the math wrong. They miscalculated how much energy would be lost due to friction and things like that, and so they needed to give it a little extra boost. And so that's why I believe they kind of MIG shifted this little tire here to push you and keep you going. Now, as we go along the rest of the track, we are still going to lose some energy to friction, so we are going to lose work as well. So we will have work going into our system, we will have work going out of our system. That's fine, it can happen. So now when we're at point C, we have to ask ourselves what forms of energy are present there. So first of all, we're at our 0 line, so we have no gravitation. But we are definitely moving. That's always the fastest part, is when you're at the bottom of a hill. So we definitely have kinetic. So if I look at this, I could say, well, let's see, how much work was put into the system? Let's say it was a big push. So I'm going to choose that 3 units were put into the system. Well, 9 plus 1 plus 3 is 13. So I have 13 units of energy now. I have even more than I started with, apparently, because that was a big push. So now I have to have a total of 13 here. Well, last time we gave friction 2, so I'll give friction 2 again. So now I'm down to 11. So that means I have to have all my 11 in that kinetic. So I have 11 units of kinetic energy because it had to go somewhere and just happens to be kinetic. So again, something I want to super reinforce, use a different color here. If we go from this point to this point, again, the total energy must, and I'll underline this time, be conserved. All right, so it must be conserved. So whenever you're looking at this conservation of energy, you look at between A to B or between B to C. If you have work leaving your system, then the total work out plus what you got at the end will all add up. So it'll all work out. So if I said, well, I started with 12, I lost 4, so that's 8, but I gained 3, 8 plus 3 is 11, so that does make sense. So you can keep track of it as a whole, but I usually recommend just picking the befores, the afters, so A to B, and then B to C, and comparing those. So like I said, you technically can't compare A to C. I would just draw a totally different not forced diagram, draw a totally different LOL diagram to keep track of that energy. So this is what you do on how to make your LOL diagrams. Okay? So again, big questions to ask. Is it moving? So if there is motion, Then you have kinetic energy. If there is height, so you're above your zero line, then you have gravitational energy. And if you have energy gained or lost, there will be work done. Again, work will go into the system if it's gained, work will go out of the system if it's lost. But those are the three main things that we're going to be focusing on. All right, don't forget to pick your system. Don't forget to choose your zero line. Without those two things, the problem is basically unsolvable. All right, so happy LOLing, and see you at the next assessment.